Okay, so it's my pleasure to introduce David McNutt, who's going to start a new series on the Cartan-Karlhede algorithm and the Cartan invariants for spacetimes. Please.
Hello. So, as the title says, I'll be working with the Cartan-Karlhede algorithm to generate what are curvature invariants, but are a special type called Cartan invariants, and I'll be applying these to spacetimes. So today I thought I would just make a small setup. I'll introduce the problem and kind of provide a motivating example. So we'll talk about the equivalence, I'll quote some things from a textbook, and then we'll carry on to actually the Cartan algorithm. I felt like argument from authority would be helpful here. And so I'll flesh out a little bit the Cartan algorithm, which is used to classify frame fields on a manifold. And then I'm going to use that actually to motivate the use of the Cartan-Karlhede algorithm, which relies on the curvature tensor and its covariant derivatives. Okay, so standard textbook entry. This is to specify my indices. So alpha, beta, gamma, these are going to be coordinate indices. So for any spacetime, it's a Lorentzian manifold. We have a coordinate system, again, x alpha to count them. I will stay in 4 dimensions. And we have a holonomic basis or coordinate basis. So we have vectors and one forms, which is a dual basis. And we can write out the metric in the coordinate space, just like one would expect from differential geometry. Now, I prefer to think about this in terms of anholonomic bases. Thank you. So what I'm going to do is pick a new basis. And this HA alpha, that should not be in bold, but apparently is the Vielbin or Veerbin. I will ask that they're dual so that I have a basis for my cotangent space, a basis for my tangent space, and their inner product is identity. That's what, unfortunately, the laser pointer won't work for the screen.
You can point with your finger.
Yeah, well, unfortunately, I don't think anyone on Zoom will see it, but that's okay. I will point my cursor with this equation. Now the coframe basis takes a very nice form. When we look at the metric, we have diagonalized, maybe isn't the best word here when we're talking about Lorentzian signature, but the coefficients relative to the basis are constant and are negative +++1. Again, this is an anholonomic frame. So here in equation A, we have the coefficients of anholonomy. They're telling you how much you deviate from coordinate basis. So again, that you might find this in a textbook, but we can do a bit more. I will quote a little bit more in the textbook. We're going to introduce a connection. The natural choice is the Levi-Civita. And so we can do covariant differentiation of a vector in a one form. And the Levi-Civita connection is defined as metric compatible. So the covariant metric is 0 and torsion free. This equation T in 12 is 0. And for GR, the thing that encodes gravity that we want to talk about is the curvature tensor and its covariant derivatives. And here, relative to the frame, it takes a very simple form. Instead of coordinate derivatives, we have frame derivatives. So this EC applied to gamma ABB is the frame differentiation with respect to, oh, that's supposed to be an H, unfortunately, bad habits. EC is supposed to be H and ED. So this is just a frame vector field differentiation. We can make the Ricci tensor and Ricci scalar. And because I'm talking about spacetimes and GR, I feel like I'm obligated to introduce the Einstein equation here in equation 16. So this, if we set it equal to an appropriate stress energy tensor, we have the Einstein field equations, and we can look at solutions to this that we think would describe the world according to general relativity. I won't say much more about that for now, because I want to go to a frame approach. So with this frame approach of looking at a frame, I can introduce a connection one form, and it is a nice tool. So this is an antisymmetric matrix valued one form. These are actually the WAB are, you could see them as elements within the Lie algebra of SO13. And we have Cartan's structure equations, so 18 and 19. And these will be relevant for the story today. But here, if I turn the torsion tensor off, I will have Levi-Civita, and I can solve for omega AC in a very nice, straightforward way. It's just linear algebra. And then I can actually, with differentiation, determine the curvature tensor, curvature 2 form. And finally, the metric compatibility condition is reframed in terms of this non-metricity tensor. And the only thing I really care about in equation 20 is that these two indices, when I bring them down, and I'm allowed to do that, that they're antisymmetric. So this is another helpful reduction of objects I'm going to keep track of when I think about this in terms of linear algebra. Now, I'm going to come back to GR and go a little further. We can modify general relativity to talk about f of R theories, where R is the Ricci scalar, so the full trace of the Riemann curvature tensor. And if we reasonably motivate our stress energy tensor, this can be generalized to a more general thing. I won't give the equation until the end, but instead I'll reframe it in terms of an action where we have an arbitrary function of the Ricci scalar plus a part that describes the matter field. And if we vary this with respect to the metric, we will have the general f of R field equations. Now, these are quite nasty. It is a small cottage industry of generating solutions and studying various theories. When people want to go beyond GR, this is something that is a natural choice. It's a very conservative choice. And of course, there are lots and lots of solutions. And this brings us to the question of, if I generate two solutions, let's say for this particular choice of f of R, do I know that they're equivalent for this theory? This theory is very, very ugly. It is possible that in the process of solving these differential equations, we actually find the same solution, or they might be different. Different is better because then you can put your name on it as a discovery. So that is going to motivate our choices here. We would like to talk about equivalence of when two solutions to GR or its modifications are the same. So let's give a formal definition for that. The equivalence problem for Riemannian manifolds, Lorentzian manifold, or a metric with Lorentzian signature, we'll say it's a Riemannian manifold, is a diffeomorphism between the manifolds themselves, so that we have the usual push forward and pull back acting on the tangent space and cotangent space respectively. And for any two solutions, we can take the pullback and we can take the metric on the barred manifold and bring it back to the original manifold. And we'll call this an isometry. And we would say that M and G and M bar, G bar are equivalent or isometric. That's a very nice definition. The practicalities of showing this can be very difficult. So I'm going to motivate a simple example. I'm going to go to Riemannian geometry with a Riemannian signature and talk about scalar polynomial curvature invariants. That's a mouthful, so I will say SPIs for that. And in Riemannian signature, if you want to characterize a manifold, you generate all of the SPIs you can possibly generate, and those locally characterize a spacetime, a Riemannian geometry, a Riemannian manifold. In Lorentzian, it's a little different, but let's try. Let's take the naive choice and try. So we'll work with SPIs, which are constructed from full constructions of tensors constructed from copies of the Riemann tensor, its Hodge dual, and its covariant derivatives. And we could think of that infinite set. Presumably, we can't compute it, obviously, only in rare cases, but we'll say that that infinite set of SPIs is script I. And here are two examples. So there's the Krushman scalar and the Karlhede invariant. Krushman is in terms of only the curvature tensor. Karlhede is in terms of the covariant derivative of the curvature tensor. That's what this notation here with the semicolon indicates. Now, SPIs are nice in relativity and string theory because they can be used to generate any sort of gravity theory you like by making an action that only consists of SPIs. So you can generate string theory, you can generate modified GR, what have you in this way. And previously, people thought that they locally characterized Lorentzian manifolds or Riemannian manifolds with Lorentzian signature. But they can't. We now know there's quite a few examples where they don't work, and I'm going to talk about one to motivate this. So we're trying to motivate equivalence or inequivalence let's take a very simple example here. So I'll take Minkowski spacetime, and I'm going to choose null coordinates for t and x. And I've written it in this more compact form in equation 27. And I'm going to compare it with something that looks like a small, maybe change from Minkowski. It's known as a homogeneous plane wave. These were discovered by Ehlers and Kunt, 65, I think. Or rather, they were classified. I think it was well discovered. It's a moot point. But here there is, in this function h, which satisfies, is a harmonic function. Epsilon is some sort of arbitrary parameter. It could be saying something about the spacetime, presumably, or conversely, this could be a coordinate artifact, and I could transform this to Minkowski spacetime. I don't know. Now, again, I'm going to repeat my message. In Riemannian signature, where we just have all pluses, in principle, if these were Riemannian metrics, we could actually say if they were equivalent or inequivalent using SBIs. And in the Lorentzian case, it's not so simple. If I denote I subscript m and I subscript p as a set of all SBIs for the spacetimes with the Minkowski metric and the plane wave metric, this is one of the rare cases where I can write down the full infinite set. It's just 0. There's only one element, and that's 0. These belong, well, Minkowski space is flat. We would say that there's no gravity there because there's no curvature. I'm being kind of fast and loose with this, but the principle I think of is physics lives in the curvature tensor. And so Minkowski space is very boring physics. In the plane wave, if I were to look at this, I would say, oh, it's flat as well. As far as the SBIs are concerned, I would say these two are the same. At least I can't say that they're different. I can't prove equivalence, and I certainly can't prove inequivalence with this. So we can go to something a little more calculation heavy. Now we have to solve some differential equations instead of just differentiating and contracting. We can talk about symmetries. So first of all, these are different solutions. And I can talk about the Killing vector fields, which are the, this is kind of abusive terminology, the isometries of the metric. Here, isometry is staying from manifold to itself, but it doesn't change the metric. And because we're working with Levi-Civita, the Lie derivative of the metric with respect to this x, which I'm going to call the Killing vector field, is 0. And that is equivalent to the symmetrization of the Killing 1 form, its covariant derivative. So the symmetrization of the indices. Now, this is an invariant object, and the set of Killing vectors forms an n-dimensional Lie algebra. And this is associated with an n-dimensional Lie group, G subscript n. And we can just compute this. So for Minkowski space, if we do this, it's not terrible. We have 10 Killing vectors with a certain Lie algebra, which I will ignore. For the homogeneous plane wave solution, we have a G6. So immediately we can say these are different. We can't say that these are equivalent. But then the question becomes, what if I take 2 of the same homogeneous plane wave spacetime, but with different epsilons? Can I say that they're equivalent or not? You could maybe make an argument that you can compare Lie algebras. Maybe epsilon appears in the Lie algebra, the structure, the commutators. And so you could differentiate it, but not always. So maybe there isn't a clear way to get that out. From a relativist point of view, talking about Lie algebra and the commutators isn't enough to say that epsilon is a physical quantity. So we can't really say, using symmetries, whether 2 G6s or 2 homogeneous plane wave solutions are equivalent. Again, physics lives in the curvature tensor. So for relativists, they would be unhappy with this. They would accept it, but they would grumble. So let's take this to a more general problem. We'll move on to the Cartan method or Cartan algorithm. So I am borrowing wholesale from Ogler's purple book, and I've included it as a reference. This is proper. So we're going to consider the classification problem for a manifold equipped with a coframe. So this is, well, I will define this in a moment, and a structure group, which I will also define in a moment. So here I'm being a little more firm about what a frame or coframe is. So if we have a smooth m-dimensional manifold, a frame on M is an ordered set of vector fields. Here I've put it in curly brackets to say that I just have a set of them, and they're indexed, so they're ordered, and they form a basis for the tangent space at each point of the manifold. And a coframe is the kind of dual concept. And I'm using dual here literally. So this is an ordered set of one forms, which forms a basis for the cotangent space at each point of the manifold. And I'm going to assume here, just so I can connect this back to the previous material, that they are dual to each other. So if I take the inner product of HA with HB, I get delta AB. If I were to write these out as matrices, they're inverse matrices of each other. And as a piece of notation, because curly brackets are kind of annoying in LaTeX, I will denote an individual coframe element with an arbitrary index and the frame basis by HA downstairs. And similarly for coframes, it'll be clear when I actually am using an individual element. Okay, so I can move on to what the structure group is, and I can actually formulate what the equivalence problem is. So we need a Lie group. That is a subset of the matrix Lie groups for the structure group. And essentially the structure group will act on the frame basis to produce a new frame basis. This is a frame bundle or a principal fiber bundle, I think. But I'm going to avoid that for this, just to keep it simple. I mean, that is the simple definition. So what we're going to do is suppose that we have a matrix Lie group G, and we're going to have two frames defined on the m-dimensional manifolds rather, M and M bar. And the G-valued equivalence problem for these coframes is to determine whether there exists a local diffeomorphism. So again, this is a pullback from, this is a mapping from M to M bar. And we're going to ask that there is a G-valued function. So this is something that takes values on the manifold, takes input from the manifold and outputs an element in our group. And we're going to ask that the pullback of H bar is equivalent to taking this G-valued function and applying it to H itself. And we're going to ask furthermore, I think this is reasonable, but here G of X is required to belong to the groups, to the structure group at each point X and M. You could foresee it kind of leaving it. Maybe you're talking about SO13 and it becomes SO4. That would be a problem. So we'll just make that requirement because we'd like to apply this to physics or relativity.
So you don't have one coframe, you have a family of coframes, which
Yes.
are just G principles bundle, right? And you equate to just
That's exactly it. Yeah, I wanted to keep it simple, but that's maybe the best message is that. So we'll come back to this, but for the moment, I'm going to do the easiest group, the identity group. And this will motivate how we will talk about the more general G-valued equivalence problem. So I'm going to suppose that I have a pullback diffeomorphism from M to M bar. Here it is in coordinates, if you will, just above equation 32. And I'm going to ask that my frame on M bar, it's pulled back to the frame on M. And if this holds, we can actually take an exterior derivative. And the exterior derivative plays nicely. We can switch the order of the pullback in the exterior derivative. And we have a relationship on the coefficients of n holonomy, which I'm going to call structure functions now, because it's easier for me. Essentially, the exterior derivative of the frame is it's a two form, and the coefficients are the structure functions or coefficients of n holonomy. Now, because of equation 33 and equation 32 that we're assuming, because this is an E-valued equivalence problem, we have that in equation 35, the structure functions between the two are invariants in some sense. They're local invariants. When equation 32 happens or holds, we can essentially, these are invariants as we'd like. And we can generate more of these. So for any invariant, for example, a structure function with particular choices of A, B, and C, these are scalars. I can do an exterior differentiation. And this works just fine for pullbacks. So again, here in equation 36 on the left-hand side, I'm doing the pullback of di bar, and that is equal to di, because these are scalars. And so I have this relationship on the right-hand side. So I can produce a wealth of invariants. I can just, till the cows come home, generate these. But I need to actually think about what their meaning is and if I can actually use them in a sensible way. So that brings me to classifying manifolds. And here it gets a little math heavy. So the first thing I'm going to do is, because I have commutator, I can talk about the lead derivative of one basis element with the other and rewrite it in terms of coefficients of anholomy. I can write any derived invariant here, C sigma, as just S derivatives here, where sigma is a non-decreasing multi-index. So we say S here is counting the order of sigma. So it's the order of the derived invariant. And now we can talk about classifying spaces. So for example, the S order classifying space associated with the manifold is the Euclidean space of this dimension, which I won't say. And the coordinates are in terms of Z, where we're coordinatizing with our multi-indices. And the S structure map that goes from the manifold into this classifying space is a map where each of the components of this map are Z sigma, which is C sigma, where the order of sigma is less than or equal to S. So this is a way of just keeping track of invariants and ordering them. It's just a little bit of accounting. And we can make a map from the manifold into a bigger Euclidean space in this way. And the map is important to us because we're going to ask that it's a regular map. So if the structure map is regular, this is saying that the number of functionally independent components doesn't change from point to point. We'll say the coframe is regular. Generally, in relativity, when we're talking about spacetime, we will assume the coframe is regular. If not, we will restrict our coordinate neighborhood to avoid irregularity. So this is reasonable. Row S here is the rank of the S structure map, and this corresponds to the number of functionally independent structure invariants up to order S. Here you can determine functionally independence just by taking exterior derivatives and wedge products to determine if you have two functionally independent components, the wedge product of their exterior derivatives is non-zero. If they're functionally independent, then it's zero. So it's a very easy way to do this. You can do it algorithmically. Now, because I've assumed regularity, I don't have to talk about neighborhoods of the manifold. I can just talk about the whole manifold here. So I'll introduce the S order classifying set. This is CS, and it's associated with the coframe HA. Oh, I left the curly brackets in, I'm sorry. And this is defined as essentially the subset from the manifold into the classifying, this K of S here, the classifying space. So the classifying space is just some Euclidean space of a certain dimension, and we're mapping in surfaces up to order S. Now, we can stop at some point. So we say the order of a coframe is the smallest integer S, where the classifying set at S order is the same as the classifying set at S plus 1. This is just talking about functionally independent invariants. I don't want to get too much into details. I'll just keep it as an argument of dimensions and leave it as is. It's, again, just a lot of accounting, keeping track of things. Olver does a very good discussion of this. But I will continue to this proposition, which is important for us. So if we have two frames on M and N bar respectively, they're smooth, fully regular, then I know that there exists a diffeomorphism from N to M bar, whose pullback takes H bar onto H if and only if they have the same order. So S bar, the order of the minimal, the order on M bar is the same as S, the order on M, and the manifolds here overlap. That's not an easy thing to actually check, but you can just think of these things in Euclidean space, and in principle, you could actually do it. I don't want to get into these details. We just asked that these two submanifolds overlap.
Don't you want that they be identical?
One would love to have that, but you can actually have cases where they don't, apparently. Again, I've made a career of avoiding this.
I know people talk about overlap, but if they don't coincide, then the structures are not equivalent.
Well, they're equivalent in a subset. So
That's
yeah.
okay, but the structures are not equivalent globally,
Yes,
right?
yeah.
Or maybe they're equivalent in a subset which doesn't include neighborhood of given point.
Yeah. So an example that would be in 5 dimensions, I think, is the black ring. So it can change signature. And when you look at the classifying manifold of this, and you look at it in a different coordinate system, depending on how you stitch your coordinate systems together and the degeneracies you have in the coordinate system, you'll get different classifying manifolds. That's what I understand. I've never actually looked at this explicitly, though, and I will say again, I've made a career of avoiding this problem.
This map should be independent of coordinate choice.
Yes, it should. Yeah, I'm trying to remember. There's something about this, but at the end of the day, if you, maybe we can talk about this afterwards. I should dig out the paper, but that's a good question. One of the reasons I like the Cartan-Karlhede algorithm is it allows me to avoid this problem as much as possible. One still has it, but in general, you can push it back as far away as you're delaying it. You can usually delay it as long as you can possibly. Okay, so let's forget about the E equivalence problem for now. We'll put it in the back of our heads, and we will think about the equivalence problem for metrics. So now I have 2 Riemannian manifolds with Lorentzian signature. Both G and G bar have Lorentzian signature. And we can rephrase the problem of finding an isometry as finding a diffeomorphism for the frame basis H that diagonalizes G, and the frame basis or coframe basis H bar that diagonalizes G bar. And then now we're just talking about a frame mapping. So the pullback of H bar using phi is something different. It's not the E equivalence problem now. We have the SO13 equivalence problem. So lambda here lives in SO13. It is a Lorentz frame transformation, and it's being applied to H. So this is a group element. I like lambda for SO13, so I will persist with this. I'll drop the G's. So this is the SO13 problem that we want to actually work with. This is what you would want to work with in the Cartan-Karlhede algorithm if you chose to work with the Cartan algorithm. But we'll actually show that we don't need the Cartan algorithm. So there's a few things that we need. So first of all, I'm going to change the problem a little bit. Here, I have a pullback acting on H bar is equal to lambda AB H bar. I'm going to now ask that I can find a G bar. So this is an N bar valued, this is a SO13 valued function of M bar acting on H bar. And on the other side, we have G acting on H. So I reintroduced lambdas here, but it's just, it looks better this way, I think. So we've basically put both frames on the same level. And what we're going to do is try to find a G bar and G so that we have new frames, H bar prime and H bar, that satisfy this property in equation 44. So now we're going to do transformations on both manifolds to try to make them line up in some way. And one thing we can do is to look at scalar invariant combinations of G and the frame. And I should also add that there are derivatives of the frame as well coming in here. But this is typically the notation that I've seen, so I will keep with it. And what we're going to ask is that at each point of the manifold, this H scalar is equal in both coordinate systems. So this is an honest to goodness invariant. And this will only hold if there is a diffeomorphism from x bar to x, where essentially here I've written equation 44, but I've introduced g bar and g again. This is essentially whenever we have a diffeomorphism that satisfies equation 44. We have this. And now the question is, well, how do we find these things? What can we do? Well, before I answer that question, I'm going to introduce another thing, which is a little bit about normalization. And we're going to talk about what we can do with these invariant combinations. So I'm going to let n denote the range of this H scalar. And because of this equivalence condition, again, I've just written equation 44 in its ugly form there in that sentence above equation 46. If I have another g-valued function, I can think of this as a pullback. So g star is equal to g bar star on as coordinates of x bar. And so if I apply that onto both sides, sorry, that's supposed to be a typo. The invariance of H implies that I can actually replace G with G star G. And the bars didn't render, I'm very sorry. So that should be G star bar, G bar star times G bar. And similar. So I have a group acting here on the first entries of H. So I have an induced global action on the range of H. I can control what's happening. And so I need to impose something. And again, this is reasonable. One can explore what happens when this isn't the case, but I will invoke it. So an invariant function, H, that is a function of the group element that I'm putting in and the frame, and its derivatives, I should say, is said to define a normalization of constant type for the coframe if for each point in the manifold, the values of the identity element and the frame put into H lie in a single orbit that is a subset of the range of H, and a single orbit of the induced action of G on the range of H. So we get like one orbit, and that's really nice. One orbit is wonderful. And the reason why is we have this very large theorem that you're welcome to read, but I can summarize as such. We can use these scalar invariants that we have to reduce our structure problem. So if we start out with a G structure group and we have an H scalar, we can choose a normalization, like I want this to be 1 or I want this to be 0. And then I can consider the associated isotropy subgroup that leaves that condition invariant. It's a subgroup, so I've reduced the size of the group, and I've reduced the equivalence problem from a G equivalence problem to GZ, a subgroup. So let's say GZ is a subgroup, a GZ equivalence problem. So each time I make one of these choices, I'm reducing the dimension of the group parameters I need to fix. That's what this theorem says. And this is why this definition of normalization of constant type is so nice. Again, we can work around this. It's just a little more messy, but we will be using this. Okay. So we're going to come back to the structure equations again, but now we're talking about the G equivalence problem, and we can consider a lifted coframe. So here I'm considering a coframe where I have an arbitrary group element applied to our H. We can do exterior differentiation. We just have Leibniz. And I can rewrite this as a gamma, which is a Maurer-Cartan form. I'm going to choose a basis for this. And the other part is the structure functions for H. Oh, I'm sorry, there's a typo in 53. That should be a capitalized H. And I can do this for H bar, capital H bar as well. And I want to point out one thing. Because I've chosen a basis for my Cartan forms, these alphas are kind of associated with the chosen parameterization of the group. The A's here are not barred. That is not a typo between 54 and 55. Those are honest to goodness constants. Now, what's nice about this is these are like before invariants. They're uglier. Well, they will become invariants, but we can compare the two and we can say something. So here, just to be a little like cheeky, instead of capital C for the structure functions, these are lower c, and there's a name for these. These are torsion coefficients. And it'll be clear why it's called torsion in a few moments. Okay, so I'm going to now assume that, so the game has always been to have a g-valued transformation that takes values at m. If we consistently specify the g's, then the Cartan forms drop down to the base manifold. So let's suppose I do that. Then the alphas here are written in terms of some sort of unknown function, z, a, with big A up top to count the group parameters. And here in equation 57, I've rewritten B. It's rather messy, but it's just this anti-symmetrization of indices where we don't anti-symmetrize over capital A. And if the two original coprimes can be mapped to each other for some unknown choice of z and z bar, I apologize. There should be a phi star on the left-hand equation. What we have then is if that happens, we can equate the two quantities, barred and unbarred. And these are something we can work with to actually normalize and absorb torsion. And I will specify what that is in a second. These are almost invariants. These will be these are pre-invariants. Actually, I should be careful. Something. We will make them into invariants. So let's look at the nice case, which is if some of these B's, for example, for a choice of A, B, and C, vanish in both coordinate systems. They have to because we're assuming they will. Then we're left with these torsion coefficients being equal. And this is what is called essential torsion for the exterior derivative of capital H of A. And there's two cases. If there's no G dependence on this torsion coefficient, it is an invariant already. We don't have to do anything. There's no normalization we need to do. If not, then we can do some normalization. We can treat this as an H, as I've talked about before, and we can reduce our group by optimistically one parameter. So we could choose it to be 0 or plus or minus 1. There is some control, and that is typically what you do. Now, the existence of essential torsion implies inessential torsion, and that means things we can remove. So we can do this process of absorption of torsion. And what we will do here is shift our basis elements of the Cartan forms by some unknown function zeta. And this is okay because we know at the end of the day, once we fix all our parameters, the Cartan forms will drop down to the manifold. So this is not terrible. But we do this and we get a new equation in 60. And the idea is that pi here and u should take a simpler form. We should be able to look at the original expression here. I'm just going to go back here in 58, for example, and be like, oh, we have some inessential torsion. Let's shift it and remove it. We can do that. This is very abstract, but generally the process is clear. So this is the kind of the outline of the Cartan method. We compute the structure equations. We check first if there is any essential torsion. Maybe we're lucky, and we can normalize it if we can. Next, we eliminate inessential torsion and recompute the structure equations. Then we go back to 1. So we again check if there's any essential torsion, normalize as much as possible, and go back to 2. And this is a sketch. Obviously, there's more to this. But this process ends when all group parameters have been specified, or a subset of group parameters cannot be specified. I debated talking about prolongation, but I think I've been vindicated now. I don't have time, so I will go on a little bit. I'll show an example, but this second case is very interesting. It's perhaps the most interesting for me. But that can happen where you don't have enough essential invariants to specify all your group parameters. Cartan, of course, thought about this and found a resolution, but we'll come back to that. So now I can kind of motivate why Cartan, Karlhede and not Cartan. And there's two major points that I care about, or at least I've been raised to care about. One is the physics, so the physicality, if you will. In GR and other gravity theories, you've heard my mantra, physics lives in the curvature tensor. The Riemann tensor is seen as physical, and its covariant derivatives as well. The frame, the coefficients of anholomy, and their derivatives are not considered physical in the same way that the metric is not considered physical. It's a potential. It's not a physical. It's not something we can measure. And in some instances as well, so there is the biggest one is kind of a philosophical or aesthetic viewpoint, which is, well, I want things that I think I can measure in my theory. And the other point is this, is in some instances, the Cartan algorithm will not be able to fix all the parameters like I talked about. So without doing prolongation. And this should say something about the symmetry group of the spacetime. Now, of course, it does. Olver talks about this, symmetries of a coframe. But one has to do something a little unphysical. You kind of, well, I will show an example, so I won't say much more about this. But in GR, we should be able to say something about something that maybe we can measure, or is related to something that can measure that maybe we can't measure, which is what we expect from symmetries in GR. Now, the other one is computational, which is maybe more important for me when I was in grad school. When I was working on this, normalization and absorption of torsion are generally linear algebra problems. They are calculation intensive. I am a fan of linear algebra, but I also know that I would like to minimize how much linear algebra I have to do in a day. It would be nice if we could combine these steps into one and reduce the number of calculations. And so what I would say is that the canonical form for the structure coefficients or their derivatives, it's not a nice canonical form. I don't think I really know how to work with that. But if I talk about the curvature tensor, like the Weil tensor, it's irreducible parts like the Weil tensor and the Ricci tensor. And even in some cases, the derivatives, I know how to work with those, and I can reduce the burden of calculation if I go to Cartan-Karlhede. So this is my motivation here. For yes.
You say you use just linear algebra.
Yeah.
But simultaneously on the same slide, you say you talk about group, right?
Yeah.
I think you should talk about Lie algebra of symmetries. Then it will be linear algebra.
Yeah.
For group, it should be polynomial algebra.
Yeah, that's actually true.
With all complications which arise.
Well, I haven't been entirely honest. In some cases as well, you have to solve differential equations. So there will be PDEs coming up. Essentially, okay, so I've had examples where, sorry, I do have to go back and just say one point about this. Here, the omegas, the alphas in equation 54, they can involve derivatives of the group parameters. Generally,
it's differential substitution, but you don't need to solve the differential equation for this.
Yeah. If there's a way to avoid that, I would love to talk about it later, because I have a problem right now that it seems like I have to solve it ODE essentially. Okay, so perhaps I will go forward. I've kind of gone a little back. Okay, so what I'm going to do is actually now motivate this, and within the last 10 minutes, this is very little about Cartan-Karlhede, but I will highlight what I'm going to talk about in the next two talks. So what we're going to do is come back to the frame problem for spacetimes or for metrics. So now our H, our elliptic coframe, is lambda with H, where lambda is an arbitrary element of SO13. Our structure equations become this. I've decided to opt to write out the Majorca-Cartan form in its glory. And one thing we can do, and this is the Cartan test, is to see if we can absorb all torsion. I'm going to assume that my Majorca-Cartan form can be dropped down to the manifold, where zeta is some sort of function of the manifold. And the Cartan test, which I unfortunately can't talk about, is to ask if I can solve this linear system. And of course I can. Here it is in equation 64. This looks very suspicious to me already, like my spidey senses are tingling. When I first saw this, because the structure or torsion coefficients are proportional to the coefficients of the anholonomy, the structure equations or structure functions. Here we have 3 lambdas, 1 lambda and 2 lambda inverses. We're just doing a frame transformation on the indices. I can rewrite this solution to the Cartan tests as some sort of combination of the coefficients of the anholonomy with lambdas applied to the indices. And that, if I really look at that, is actually the Levi-Civita coefficients. So those are the connection coefficients for Levi-Civita, and then Lorentz transformed. And so what I'm going to do is actually I'm going to do some prolongation without talking about prolongation. I'm going to consider a new frame problem on my manifold, which is M with the direct product of, oh, sorry, that's supposed to be SO13. I apologize. This is a bad habit. So OM is supposed to be SO13. And so on M, we have our basis HA. And on SO13 or OM, as I've written it here, we can work with the forms here. So these are the Maurer-Cartan forms, which have been shifted by this Z function. And here, if we do their exterior derivatives, we find that we have something that almost looks like the Cartan structure equations. It's going to be the Cartan structure equations. So we have the exterior derivative of H, big H. We have the exterior derivative of these objects, which are 1 forms, but have 2 indices. That's okay. And more precisely on M1, we again have those things, but what I've done here is I've written out omega AP, this connection 1 form. And to me, maybe because I was raised on Nakahara, that looks like a transformation rule for connection coefficients, if I were to fully flesh it out. So if I took that exterior derivative and wrote it in terms of capital H and derivatives of the components, I would have the transformation rule for connection coefficients. And this S matrix looks like the lifted version of the curvature tensor of the metric. I could actually even write it out into the original formula. I've chosen not to for space. And we've actually found a theorem, Olver has derived, we've talked about a theorem by Christoffel, which is a complete set of structure invariants for a Lorentzian manifold are provided by the invariant components, the higher order curvature tensors. So they're just their covariant derivatives as we normally would do, up to S+1, which is the order of the manifold we need. And in the regular case, 2 Riemannian manifolds are locally isometric if and only if their curvature tensors parameterize overlapping classifying manifolds. Now, this is where I said, you can't avoid it. It's still here, but we've put it off to as far as to the end as possible. And in most practical cases, comparing classifying manifolds isn't too terrible. Yeah, and again, the order of a Riemannian metric is merely the order of the coframe, as we've seen before. Okay, we're nearing the end. 10 minutes left, so that's perfect. I can't believe this worked out. This is the Cartan-Karlhede algorithm in its glory. It took quite a while to get this. I wish I could talk about the story of how it was derived, kind of some of the failures with getting to this. But what we're going to do is denote the set of components of the curvature tensor, its first covariant derivative, up to its qth order covariant derivative as RQ. So the algorithm starts out, we start at Q0, we're computing the curvature tensor. We fix the frame as much as possible using Lorentz frame transformations. So here we exploit the Petrov classification for the Weil tensor, or the Segre classification for the Ricci tensor, which we can treat as a matrix. And that allows us to fix the frame in a canonical way. We then look at the invariance group. So this is the linear isotropy, is what we'd call it. And these are the Lorentz frame transformations that leave the form of our metric, the form of our curvature tensor, So let's split it, Weil and Risi, unchanged. We record that number, the dimension. We then find the number of functionally independent components among the elements of the Weil tensor and the Risi tensor. And then we go forward. So we compute the first covariant derivative. We compute the covariant derivative of the curvature tensor. We try to fix our frame using the remaining frame freedom, so the elements of H0. We determine the dimension of the invariance group. We determine the invariance group. So this is the frame transformations that leave the curvature tensor and its first covariant derivative set up in its canonical form, invariant. We find the number of functionally independent components, and the algorithm repeats. And it tells you to stop when the dimension of the linear isotropy group stays the same, and the number of functionally independent invariants from the previous iteration is the same. So if TQ is equal to TQ minus 1, and the dimension of HQ is equal to the dimension of HQ minus 1, the algorithm tells you to stop. You have all the geometric information you need. Now, you have two discrete sequences, and they can help you say if two spacetimes are inequivalent. And then you have a wealth of invariants. You have all the components of the curvature tensor up to order p plus 1. So this is a huge classifying manifold. You can usually reduce it by only looking for algebraically independent components. But at the end of the day, this is a mess. And if you have two spacetimes and their sequences of HR, the dimension of HR from R is 1 to p plus 1, and the number of functionally independent invariants, TR, from R is equal to 1 to p plus 1 is the same, you then unfortunately have to start comparing invariants. And the classifying manifold is RQ. Now the set RP, relative to the frame basis we've determined, is the Cartan variance. These are Cartan variants. Now I have a little bit more time, and I'd like to use that to actually talk about what I'll talk about in the next two lectures. And these are things that, as I said, allow me to reduce the amount of linear algebra or computation I have to do. The first one is a choice of frame. I'm going to work in a complex null frame basis. So this is L, N, M, and M bar. I've complexified my transverse space, and I've chosen L and N to be null directions. So this is in a very compact notation. And the reason I like this is because for a null frame, the Lorentz transformation group is much simpler. Boost and spins are just multiplication by a scalar for a boost, and e to the I theta for a spin. That's just a rotation in the n. And null rotations about L and N take a very simple form, where B and C are complex parameters. So these are complex functions of the base manifold. And in addition to a simpler form for SO13, I think it's simpler. Maybe some people might disagree. We can use this basis and shift the problem to spinners. And spinners are great for taking an ugly tensor problem and working with spinners makes it so much simpler. So this is the Newman-Penrose formalism, and I will outline some of the details that make working with the Cartan-Karlhede algorithm in 4 dimensions easier. I'm just going to go back now. That is going to help us find the invariance group of the frame. And it will also help us with, with step 3 and step 4. So finding the canonical forms and finding the invariance group. But actually finding the canonical forms beyond the curvature tensor is a little problematic. For a very long time, we did not have canonical forms or a way of really sensibly classifying higher order derivatives of the curvature tensor. And so what I will also discuss is the alignment classification. So we can use the alignment classification, and it relies on a boost. So again, I'm sorry for flip back and forth, but we will use a boost here in equation 71. So we'll ignore the spins, and we just have this lambda. And for any tensor written in this basis, we have a boost transformation for a tensor. So this is a tensor of rank n, and we're taking an arbitrary coefficient, and we can count what the powers are of lambda here, R. It's this quantity called the boost weight that I've written in equation 74. But it's a scalar with n indices, a1 to an, of the frame component. And now what's neat is this in itself is not invariant. The boost order, which is the maximum boost weight of a tensor for a given null direction, is kind of an invariant of a null direction if you want. It's a unique quantity. For each L, we get a boost order. And if we can minimize the boost order, that is something that we can use to classify a tensor. So the alignment types of a Weil tensor or Ricci tensor, both can be classified into 6 types. There's G, where the boost weight is 2 at most. And in 4 dimensions, you can always make this into boost type I, where the boost weight is 1. And then we have further lower specializations. So if you can find an L direction for a tensor where the boost order is 0, it's type 2. If it's -1, it's type 3. And if it's -2, it's type n. And perhaps the easiest one is if the tensor vanishes, then you have alignment type O. So that's probably the best one. So what I hope to do is to talk about the Newman-Penrose formalism, the alignment classification. This will make the implementation of the Cartan-Karlhede algorithm easier, and I will talk about some examples in the next talk. These are the references. So since I stole so much from Oliver, I feel like I definitely have to cite them. And then one of my favorite papers on the alignment classification by Milson, Coley, Pravda, and Pravdova. Okay, thank you for your attention.
Thank you. Are there any questions or comments for David?
Andrea? Oh, he's clapping.
That was a clap.
Thank you.
No, I don't have any questions. No, thanks.
Can you go a couple of slides back? Yeah, that's okay. Just a bit forward. Right. So, I was willing to ask the Cartan invariants, right? So, where do they live? On the bundle, or we would like them to say to see them as function on the base matrix?
Well, the quirk is this. I would say that they live and they're lifted up. But because of a good specification, sorry, I just need to find the actual definition. If we can do a good specification of the group parameters, they drop down. They can be seen as invariants on the manifold when you pick that frame. But I would say they live upstairs.
But then, well, I was thinking the point actually of doing it carefully so that you involve structure group and normalizing that you actually can push them down.
Yeah.
That's it. So.
But even then, they
Because
still live
on the
upstairs. They just.
You actually uses your structure. Yeah, why do you need all of this? You already have invariants upstairs. All your structure functions and the derivatives. That's a bunch of invariant upstairs. They are actually invariant. Every component is an invariant function upstairs. Of course, this thing is not equivariant, or even what's wrong? It's not invariant along fiber, so you don't push it down.
Yeah.
Right. So components are invariant functions upstairs. You cannot push them down. But I think the point of Cartan-Karlhede was actually to push some of this down.
Yeah, so I would say that because of the covariance here under Lorentz transformations, in some sense, I mean, I would still argue that they're both. when you fix the frame fully, when you fix the frame up to some non-trivial linear isotropy group, because the components of the curvature tensor and its higher orders no longer depend or is no longer affected by these other parameters, you can treat them as dropping down.
Yes,
Yeah.
so even though if you still have isotropy and stabilized and you still have isotropy,
Yeah.
The functions which you obtain in this way, they are projectable. If they're not, then the differentials are not preserved by isotropy, and you have to have drop on the next stage, not stabilized in Cartan-Karlhede.
Yeah, but that never happens. You can always either you will always either have no isotropic group, linear isotropic group, this HQ, or you will have a fixed dimension.
Yeah, you have to regular case, but I mean, if you
Oh.
don't have isotropy, that's clear that you sit on the base. But the question is, if you have isotropy, I understood that these are still functions actually downstairs.
Yeah, I mean, the view is this, is that they are, because the remaining lifted coframe has no effect on the curvature tensor. I mean, formally they do. You can still apply, let's say if you had spherical symmetry, you have SO3 isotropy. You can still rotate as much as you like your frame, and it won't have any effect, but the curvature invariance will not change. Yeah, so it is still, in some sense, lifted, but in practice, I would say that you can drop that down, that piece, you can project it.
The functions are projectable. So I mean,
Yeah.
I don't know what practice or not practice, but they are just projectable functions.
Yeah.
Of course, one especially have to a bit care here about like connected components and things which are like local, but maybe have to be actually global along the entire fiber. Then you can say projectable. That's a bit things like people, but I think that you have to be with respect to structure group, you have to be global.
Yeah, and as a rule, people like, for example, for canonical forms in step 3, people usually assume Petrov type or Segre type does not change in a neighborhood. So there could be interesting questions of where Weil type changes, and then what do you do? And it does happen, like Reisner-Nordstrom. There is a hypersurface where it becomes conformally flat. So it's like, how does the classification work there? I mean, it works fine, but like, again, I mean, it works fine as long as you ignore the surface. Yeah.
And that's a different question when we talk about regularity. I agree.
Oh, yeah, sorry, yes.
Any other questions for David?
I have one. If you go 1 or 2 slides back. Yeah, no, 1 slide. 230. You go to 2 slides forward.
Number 30.
30.
30, okay. Too fast, sorry, yeah.
So this theorem,
Mm.
is it about both Lorentzian and Riemannian manifolds?
Yes.
So
I think actually it applies to Pseudo-Riemannian. I think this is, well, Christoffel, I think, originally framed it in Riemannian manifolds.
but the last segment does not hold for Lorentzian manifolds. Or
That's the question whether you consider those functions on Cartan bundle. No, no, wait. No, that's still true.
Here, this is talking about Cartan variants.
That's not scale. That's not polynomial variance.
So here, you're talking about the curvature tensors and their covariant derivatives.
That's in regular case. Well,
Yes, in regular case, of course.
the only thing which is not true here is this overlapping thing. But I don't agree.
okay, so could you just replace Riemannian by Lorentzian in the last sentence?
Yeah. In fact, that's what I should have done. I'm sorry.
Okay.
Again, there's also this view that Riemannian manifold can be Riemannian manifold with signature. So, okay, yeah, but that was a typo on my part. I'm sorry.
Any further questions for David? If not, let's thank him again.